The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
And our next speaker is Dr. Bohwan from Daewoo Engineering and Construction. Co-authors are here. Dr. Ha, one of the co-authors here, and Dr. Oh is talking about BIM for tall building construction, especially on that movement prediction. And he got his PhD degree from Lehigh University. And he's been in the research and practice over many years. So I think it'll be a really interesting topic and informative. With that, I'd like to introduce Dr. Oh.
Thank you, Professor Kang. Good morning. It is my great honor to be here as one of the speakers. Let me talk about building movement during construction. As he already asked the question, but okay. In chapter one is about building movement and its adverse effects and the solutions, followed by the building movement control technology. And in chapter three building projects will be introduced as application examples. No equations in my presentation, just kick back and relax. This is Northeast Asia Trade Tower, the second tallest building in Korea, of which height is about 305 meters. Is it really 305 meters? The answer is no. By our analysis and monitoring of column shortening, the building is about 8 inches shorter than the design height. Burj Khalifa. We believe it is standing above ground as a vertical structure. Unfortunately, it is not. From the beginning of the design stage, it was anticipated to move laterally by 4 inches. And the result of GPS survey during construction confirmed it. Marina Bay Sands, world's second furthest leaning building in Singapore. To control lateral movement, presets, temporary steel strut, and vertical stressing were used. Capital Gate in Abu Dhabi is the world's furthest leaning building. Presets and vertical pre-stressing are also used to control lateral movement. As you can see in this animation, the core of this building was built to the opposite direction, from which it is expected to move. You could possibly think that the amount of the movement is not a big deal compared with the overall dimensions of the building. We can hardly recognize the movement. Then, why is this actual or lateral movement of high-rise buildings important? It's a matter of incompatibility. Building components attached to the structure, such as pipes and elevator rails, don't want to move. However, as you saw in previous slides, structures move in many cases. And the structure itself doesn't move equally. That at some points, a stress develops, which was not estimated in the usual structural analysis. The solutions to these problems can be found at design or construction stages. At design and engineering stages, we can design structural members for additional stresses due to the movement, or for equal stress distribution by adjusting sectional dimensions or selecting materials which have appropriate strength and stiffness. If it's too late to change the design, we can use delay joint or adjustment joint, where the problem is expected to occur. As a final result, compensation or preset is applied during construction. The Trump Tower is shown on the left. Due to the great amount of additional stresses from differential shortening between core wall and columns at irregular level, the structural designer redesigned the core wall using the straight-and tie model. Now, Chapter 2, Building Movement Control Technology. As shown in previous slides, the building movement is very important, and its prediction is necessary for precise and safe construction of high-rise buildings. The construction stage analysis occupies the essential position of the building movement prediction, and it can simulate sequential real-world load application, creep and shrinkage effects of concrete, cumulative displacement, deformation and member forces, and effect of temporary supports. However, the analysis itself is not enough and should be complemented by material testing, field measurement, and survey. Around 2007, our research team tried to use the programs shown here for the construction stage analysis of tall buildings, but we found them to fall short of some of our expectations, especially in modeling and analysis features. So we have been developing our own in-house programs. As you can see in this animation, this program is able to simulate actual construction sequences and perform iterative structural analysis at required construction stages to give the history of the stress and the deformation of every structural member, as well as the movement of the entire building. This program automatically calculates the differential movement. Most of the adverse effects from building movements arise from their differential values, not from their absolute values. Although shown exaggerated in this diagram, this differential value is accumulated to several inches at upper levels of tall buildings. What is worse is that differential shortening of vertical structural members makes the building deviate from verticality by a mechanism similar to the bimetallic effect. This program is also able to divide the movement based on the sequence of construction. Divided components are so-called up to and sub to, depending on the duration in which the movement develops. From this example of a three-story building, the second and the third level shall have vertical movements even before they are constructed. These are up to movement at each level. The movements will further develop after each level is constructed, and they are called sub-to movements at the target day. To make the building reach the designed height at target day, preset is required during construction. If we construct each level at designed height, only sub-to movements at target day will remain, and the preset amount shall be reduced. Division of the movement is important in that we can precisely evaluate the components of movement, which develops the adverse effects to the building elements and can take corrective measures according to that. Our program has the algorithm to divide the movement based not only on the structural construction, but also on construction of non-structural elements, such as elevator and facade. This algorithm is a registered patent in the United States. The fundamental difference of construction stage analysis from ordinary structural analysis is the consideration of aging effect of concrete. During the analysis, our program calculates modulus of elasticity, creep and shrinkage developments based on several state-of-the-art code provisions such as ACI, PCA, and Eurocode, and famous researches including B3 model and GL2000 model. Basic creep and shrinkage values are then modified to consider the effects of member size, relative humidity, age of concrete at loading, and residual strain due to reinforcement. Creep and shrinkage properties of concrete specimens are acquired from the climate chamber test and will be provided for the updated analysis. To verify and modify the analysis, vibrating wire gauges are usually embedded in or attached to concrete members to measure the history of deformation throughout the entire construction period. A strain gauge installed at the center of a mega column is shown here. Data loggers record the member deformation and send data using wireless technology for analysis. Last chapter introduces 3 applications. First application of our program was made to Kuala Lumpur City Center project, which is located right next to the Petronas Twin Tower. As shown in the photo, the building mass is eccentrically arranged in vertical direction. Therefore, the building was anticipated to move to the right-hand side during and after the construction, as shown in the animation on the left. The maximum amount at the roof level is about 5 inches. Cooperating with the professional surveyors, the building is constantly built at the design location in plan. Consequently, only sub-2 movement is developed. So, the shape of the movement becomes different from the total movement, as shown in the animation on the right. The maximum amount is also reduced to about 3 inches. Construction stage analysis was used to identify the need of temporary supports for a transfer girder, shown inside the circle. In the developed program, not only the birth date of elements, but also expiration date can be designated as a critical construction sequence. The temporary supports were modeled to be removed after 13 months, as required in the particular specification. This graph shows the vertical displacements of 3 nodal points of the girder. According to the analysis, the girder is equally sound with or without temporary supports. So, the temporary supports were removed from the construction site, and about $50,000 were saved. Compared to the measurement using sensors, the overall movements of a building can be easily captured by surveying the as-built condition. Although visual inspection is the usual way of surveying, it heavily depends on the naked eyes. So we have adopted the 3D laser scanning technology to survey the verticality of the elevator shaft, as shown inside out on the right. As a research purpose, 3D laser scanning technology was also applied to a survey of tall building. It is known to be the first trial in the world. The biggest problem posed by the vertical deviation of a building is related to the elevators. The elevator core should be vertical for the installation of elevator rails, and the rails should remain vertical for the guaranteed performance of the elevators. These graphs show the lateral movement of the building along with the elevation at 3 different stages of construction. Blue bars are the movement up to the construction of a structure at each level. Red bars are the movement after construction of structure until elevator installation. And green bars are the movement after installation of elevator up to 7 years of completion of construction, as specified in the contract documents. So, since the tower is constructed at design location at each level, the blue bars disappear, as you see on the right graph. The elevator core needs more space of maximum 2.5 inches to install the rails. And the predicted values generally agree with the survey results and 3D laser scanning. Although the values are not exactly the same, the variation of the movements follow the predicted pattern, and the difference are acceptable in terms of construction. Second application was made to the I Tower, which will be used as a new UN office building in South Korea. 150 meters is not so high in terms of building movement. Construction challenge is in the column-free area called the Sky Garden. Although not visible in the ordinary structural analysis, if this area is constructed without any temporary support, the intermediate levels shall sink excessively, as shown in this construction stage analysis result. This animation shows the final version of the temporary supports and erection method provided by our research team. A strain gauge is shown in a yellow circle as attached on the flange of a temporary column. Strains measured at every hour during the Sky Garden construction are shown here. The strains were all within 10% of the proportional limit, so the structural safety and stability were guaranteed. Like the KELCC project introduced earlier, I-Tower was also digitally scanned, but this time the Sky Garden was scanned 6 times to see the progress of movement during construction. And the scan points were predetermined as shown in this picture to easily process the massive amount of scanned data, so-called point cloud. When the predicted values were compared to the survey results, the difference in deflections at the most concerned 2 points, which is on top, in this picture, were only 1/6 inches. In this project, we also tried to extract a 3D model from the scanned point clouds. It is currently an experimental stage in our research program. Combined with the building information modeling, it will become a powerful tool to evaluate the as-built condition. As a final example of the application, let me introduce the IB Tower in Malaysia, designed by Sir Norman Foster and being built by Daewoo ENC. This 274-meter building is mainly composed of RC mega column and bracings connected to the core walls. Seemingly symmetrical, but eccentric core walls make the columns on the opposite side shorten more than the other columns. The result is the permanent leaning of the building about 4 inches as shown in the animation. In the left graph, up-to and sub-to components are shown in red and blue, respectively. They look equally significant in amount, but different in their distributions. In terms of the cause of the movement, as shown in the right graph, the elastic movement due to the accumulated loading, shown in blue, occupies more than 70% of the total. The rest is mostly clip, shown in red, and the shrinkage movement, shown in green, is negligible. To make the building back to the vertical condition, 2 preset options are available. One is to preset for the total movement, and the other is to preset for only sub-to movement. During construction, the preset is applied by moving or tilt the formworks in the preset direction. Upon application of either method, 1/2 inch of residual movement will remain. After considering the survey method planned for the construction, preset for sub-to movement was adopted. The up-to movement shall be compensated at each level by constantly relocating the design coordinates. By this way, the preset can be done more precisely and effectively. My presentation has no conclusion. However, a smart audience like you can catch the point. Building movement issues, I'll be more than happy to help you. Thank you so much for your attention.
Thank you, Dr. It was like a business talk, but excellent presentation. Yes?
Thank you very much. This is very interesting. There's so much material. But I'll just touch up on the first thing as a designer, I would be interested in at which point the company takes over the design and becomes their own, and what kind of interaction happens before regarding the construction staging. And maybe you can comment, what's the minimum or the minimum that you would compensate? Or is it at every story, every other story, in practical terms?
Well, thank you for your question. The first question, it depends on the project delivery type. There are 3-4 different project delivery types as usual. For design build, we can get in from the first stage, or, well, IPD is not available in Korea yet, but for the design bid build, we jump in at the very later stage, right before the construction. So, it depends on the project delivery type. The second question, the minimum amount of preset or the correction is about 20 millimeters, say, less than 1 inch, because the construction tolerance is about less than 1 inch. Can I answer your question?
Any other questions? Thank you for your comment, Dr. Ha, and the excellent presentation.